Hello, my wonderful physics classmates. Today I'm going to be going over Lab 3 of 2212. So let's get right into it. This one has to do with bar magnets. So, the purpose of this lab was to observe the magnetic field created by a bar magnet at different locations on axis and off axis. These observations would be used to calculate the magnetic moment, which we calculated to be 8.7841, and create a model on GlowScript to simulate the experiment. Now, let's go on to the procedure. So the system was the smartphone and the bar magnet. So what we had to do first was find the position where Earth's magnetic field on the x-axis is 0, and place the meter stick on this line. Then we placed a bar magnet on the table with the meter stick against it on axis. Next, we find the location of the sensor chip on the smartphone by moving the phone around along the meter stick and observing the changes in magnetic field. We measure the magnetic field at several locations on the meter stick, and then finally we measure it at a distance of 45 degrees from the magnet. So our key concepts all have to do with magnetic fields around a dipole. And you know what's pretty cool? Some birds can detect magnetic fields in order to navigate. Isn't that awesome? That's just great. So for our magnetic field equation, we have Br equals the magnetic constant times 3 r hat times r hat dot the magnetic moment minus the magnetic moment over r cubed. Now, the results of this experiment was that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And the magnetic moment, as stated previously, was calculated to be 8.7841 angstrom meter squared. So let's take a look at the code. First, up here we have setting some constants, and then we have creating the magnet as an object, inputting our calculated value for the mu. Then we have a function to take the magnetic moment and an r value and calculate the magnetic field at this location. Next, we have a factor to scale the arrows so they're actually visible. And then we have setting up just a baseline distance that will be used. So here it's 20 centimeters. So here we set up the different observation locations where we're going to be measuring the magnetic field. There are 2 on axis and 4 off axis. Here, the arrows for the magnetic fields are calculated and created and scaled based on the scale factor we set earlier. So we have 2 on axis here and then 4 off axis. Next, we have a magnetic field arrow created at 45 degrees based on where we measured for the experiment. This was calculated in the same method. So here are our results. It's hard to fit all the arrows on the screen because of different sizes and distances, but here you can clearly read the different magnetic fields of each. Here we have some similarities and differences between the model and the experiment. In the experiment, the magnetic field magnitude and the distance from the magnet were found to be roughly proportional when distance was raised to the negative third power, as shown by the graph here. And for a 45-degree measurement, in the experiment, the magnetic field was this value right here, and then our model was this value right here. So our model doesn't take into account any Z magnetic fields, and this was just created based on our surroundings and not by the magnet dipole itself. So these can pretty much be ignored in our analysis. But we got the values to be relatively close to each other for the X and the Y. So some source of error were outside fields created by surrounding metal and electronics, and then not finding the exact location of the magnetometer chip in the phone. So what if 1? Without accounting for Earth's magnetic field at the start of the lab, our measurements for the X components of magnetic field would have all been off of their true values, which would have affected our calculated magnetic moment and N values. And what if 2? Sticking 2 identical magnets together would have greatly dampened the magnetic field created, as the field lines from each magnet would be opposing, and this would create destructive interference. Thank you for watching this lab presentation. I hope you have a wonderful night.